transducers. And what is a transducer? Yeah, but what's it do? Excuse me. I'm listening. So what does a transducer do? Huh? What does a transistor do? Saying just something physical into an electrical equivalent, right? I understand. We have digital sensors and we have analog sensors. Of course, the photoresistor is an analog sensor, and the photovoltaic cell is an analog sensor. The thermistor is an analog sensor. So this guy here does what? It varies its resistance with temperature. That's what I'm looking for. That's what it does. You're right, it measures temperature, but it varies. How does it measure temperature? Well, it varies its resistance for temperature. Photoresistor, what does it do? Yeah, varies its resistance with light. A photovoltaic cell or a solar cell does what? Yeah, outputs a voltage proportional to light. And then what does a Hall effect do? Not metal. Hall effect. If you put a Hall effect sensor up against a chunk of metal, it's not going to do anything. It could be used to measure the RPMs of the motor, but what does it do? I mean, we got a lot of things that would measure. I could use a DC generator to measure and that's a tachometer. A DC tach is nothing but a DC generator, and it measures the RPM. The output voltage would be proportional to speed. It measures the strength of a magnetic field. So a Hall effect measures the strength of a magnetic field. It does not find metal. Now we can make it appear to find metal by putting a magnet in front of the Hall effect, right? And then putting a chunk of metal in front of it, and it'll concentrate the field and call the field to change. And the Hall effect would measure that. Another use for Hall effect sensors, we can measure AC current indirectly by using something called a clamp-on ammeter. Have y'all seen those before? And those work just like the secondary of a transformer. That's all they are. So the change in magnetic field would induce a voltage into the clamp-on ammeter that would be proportional to the current, right? Y'all understand that? But those clamp-on ammeters will not indirectly measure a DC current, but a Hall effect sensor will. So you can buy clamp-on ammeters that will measure DC, but they're going to be pretty expensive because they have a Hall effect sensor in there that measures what? DC current. And it's not measuring the current, it's measuring the what? The strength of the field, and the strength of the field is directly proportional to the current. I mean directly proportional. We have two types of Hall effects. We have analog and we have digital. So digital is actually a little it's actually a little integrated circuit. We call them latching Hall effects, and they're really, really neat. And we had Hall effects here, and I didn't know exactly what there was, and didn't have a data sheet on it, so I looked it up, and we'll look at it later on and see. So what we got here, we got the little Hall effect sensor right here. And then on its output, I have an LED. And then what do I have here? I got a magnet. Now what a latching Hall effect does is one polarity will turn it on and it latches. And I can put this polarity on there all day long. What turns it off is the opposite polarity. So a north might turn it on and a south will turn it off. And it latches, so what it means is it would stay on how long? Forever, unless we lost power. And if we lost power, of course, it would come back up to its default position. See, which on this situation is off, right? So, and they would tell you which one. So So one polarity does what? Latches it. Notice all I'm doing is doing what? Turning my magnet around, and this would turn it off. So we call this the latching Hall effect. An analog Hall effect would actually, if I was to look at this, the output would change with the actual output would change with the strength of the field. And I didn't know what time we had. I finally figured out how to wire it up. I told you I was going to figure it out. It's pretty neat, ain't it? So you could use it to measure speed. So what you do, you'd have two magnets on something that's moving, and one would turn it off and one would turn it on, right? You understand? And then you could use the frequency to calculate the frequency of the pulses to calculate the revolutions per minute, which is pretty neat. So you'd have one pulse, one on and one off per revolution. Take that count, multiply it by 60, and that would give you the revolutions per minute, right? So that's a Hall effect. I should have hooked up some of these photoresistors and stuff to a resistor and actually seen us vary the voltage. So this is actually an integrated circuit right here. So a Hall effect has to be powered up. That's why it's got 3 pins on it. So a Hall effect will not work unless it's got power. So this is what my power supply is coming in for over here. So I got my power supply turned in, and it's powering up the Hall effect, and then the output uses the same common. That's why it's got 3 pins. So the output and the power supply uses the same common, which would be this guy right here. Pretty neat, huh? So we could do this, and it's a non-contact sensor. So the sensors we've been looking up so far would be what we refer to as non-contact sensors. And most of your solid state sensors are non-contact, which means what? The device that we're sensing does not have to touch the sensor. So we looked at a varactor, which is a diode. It acts like a variable capacitor, but we vary its capacitance with a DC voltage, right? Pretty neat device. And then we looked at a thermistor, which varies its resistance with temperature. The only problem that it has, minor problem it has, is that it's non-linear. And what does linear mean? Yeah, it means its output would vary its resistance would vary in a straight line, but it don't. So it varies in this curve. It's a parabolic curve, right? And of course, we use these all the time in thermostats for houses. And we get by with these because the range of the temperatures that we use in a house are so limited, right? But we also can buy integrated circuits like an LM35 or an LM34. One of them, but you have to power these guys up, and what do? They compensate. They have the thermistor in there, and then they actually compensate, and they will give you a output voltage that is proportional to temperature. Now we got some back there. We might fire one of those up and see what they look like. A photoresistor. These guys are all over the place. All our street lights have them in there now. If you got lights that turn on at night, they're in there. Motion detecting lights, they have these in there so it don't pick up motion during the day. These guys are all over the place too. Photovoltaic cells, what most people call solar cells, these guys actually convert the energy of the light into a voltage, right? Voltage and a current. So this is our Hall effect sensor. So this would work. This guy here would work on that, but one of the magnets would be a what? Would be a north, and the other magnet would be a south. And this guy here would sense the speed of it. So these guys don't sense speed, they sense what? Fields, right? Magnetic fields. And this shows you a connection right here. And we'll learn about this output too. So this guy here don't output he uses a transistor, and we'll talk about syncing and sourcing and that kind of stuff later on. Talk about liquid crystals, which are not in your book. We just do this in there to understand these are nothing but solid state devices that are really, really neat. And let's all look at the microscope and look at the actual display, right? You can see the little lenses out there that light up. Pressure switch, I got those LEDs. So what happens when we forward bias these diodes and these junctions, these electrons are falling into the holes and the holes are filling up. Anytime that happens, these guys release energy. They release energy in the form of light. The problem is that on germanium diodes and silicon diodes, this energy released is at a wavelength we can't see, and there's not enough of it to see. So germanium and the silicon junctions are would make a very poor, well, they would make an LED, right? You understand that? So germanium and silicon release very few photons, and these semiconductors impede the release of the photons. So we don't use this. We use a semiconductor called gallium. For this reason, LEDs are made from gallium, and then we dope them with something else. And of course, this shows you, this picture is not in the book, I don't think, but this shows you the energy that's released. So what we got to do is we got to have a lens. On an LED, we got a lens. And you can see the little wires going up to the junction. They're really, really small. Most of these things you can really see them. So you're not seeing the junction. Some of you can see better. This one you can see through pretty good. We haven't looked at it under the scope. We might try it and see what we can see. You might see the little pad in there. You can't see a junction. So what they do is they mount the little LED on one pad, and then they run a little tiny whisker into the other side of the diode. Oh, I see the whisker. Yeah, you see the whisker. Pretty good. Tiny. Yeah, it's tiny. Contrary to popular beliefs, the color of the lens does not determine the color of the LED. The lens only enhances the color of the light emitted by the junction. I wish you'd have brought yours in, because yours also. Oh yeah, I gotta grab that. Yours has clear lenses on it, yet it does 3 colors. Yeah, red, green, blue. Yeah, we'll get Wesley to bring it in last class. You know. The lens only enhances the color of the light emitting by the PN junction. The color emitted by the LED is determined by what we dope it with. So we take gallium and when we dope it with something, right? You understand? And then that doping determines what wavelength comes out of the junction, and then that determines the color that we see. You know, the ones that Wesley's got is really neat. They're tri-state LEDs, or they're red, green, blues, and that's what we use. And a lot of these big signs that you see, in fact, they are. These big signs you see on the side of the road are nothing but thousands of LEDs, high-intensity LEDs. They used to be colored light bulbs, but all of them now has gone to LEDs. That's all they are. So if you used to get right up on them, like using this magnifying glass, you could see them. And sometimes you can. You can actually see the dots. But you're back far enough that your eyes do what? Blends those colors together. So gallium arsenide creates a light around 900 nanometers, which is in the red range. Gallium arsenide, 660 nanometers. Gallium phosphide, 5. By the way, in light, we don't give in frequency. When we send stuff in waves, so light is electromagnetic waves. No, that would be, lumens are intensity. They're not the color. Lumens is how bright the light is. And then colors, but if we were to come up here on these magnetic waves, these things traveled in length. Y'all understand that? These are electromagnetic waves, so it goes up, and then it drops down. Well, the distance between any 2 points, so let's just go from here to here, would literally have a length. It's just like on the ocean. You know, if the waves were perfectly lined up, that would be a frequency, right? They would be occurring at a rapid rate, but you could if you could move with them, you could measure the difference between those waves. And that would be what we call a wavelength. Well, light frequencies are not given in frequencies. They're up in the terahertz. I mean, they're way up there. So normally what they're given in what we call wavelengths. And this is even popular in ham radio. I don't know if you ever heard of 2 meter. If you got your 2 meter license, well, guess what 2 meter is? That's the length of the wave, moving at that frequency. So ham has that. And by the way, when you transmit your antenna's got to be in a wavelength. It's got to be in what we call a quarter wavelength. If you was into CB radio a long time ago, they called it SWR, standing wave ratios. And what you had to do is you had to adjust the length of your antennas till you got a certain wavelength, so it was hitting the end of the antenna right. Yeah, so if you're into radio, ham radio, or anything like that, you understand wavelengths and standing wave ratios and the lengths of antennas and everything. So the lengths of antennas for transmitting, not for receiving, for transmitting has to be in quarter wavelengths. It could be 1 wavelength or it could be in a quarter wavelength. Anything between it, you would burn your radio up. And we're not going to talk about why, but you would. So these, around 800 nanometers is red. We can look at that. And the bigger wavelengths with these. So some of these you can't even see. I'm sorry, these would move toward green or blue or white or something like that. By the way, it took them years to get white. I mean, that was something they worked on for years, trying to get white. And I can't remember the guy. I wish I did, but he actually won a Nobel Prize of Physics because he invented the white LED. And now we don't even think about it. We had bright blue for a long time, light blue for a long time. I don't know, a lot of your cheap flashlights you buy don't put out a white light, they put out a what? Blue light. But now we got white, thank goodness. And eventually our whole lighting system is probably going to move to that. But this is around 500 nanometers. This is red, and these start moving up the light. So these tell you the colors. So 900 nanometers would be in the infrared range, which would be this guy right here, right? So this has got an LED in it. You can actually see it right here, but you can't see the light when I flash it. Can you see it? It picked it up. I forgot it had a sensor in the back too. So all we're doing here is just sending out a sequence of pulses, and the sequence of pulses represents what? Which button you press. That's all it is. And every remote sends out, if your remote sends out a different sequence, then they won't interfere with each other. So we use a lot of infrared. All your remotes for your TVs and your DVDs and all that kind of stuff, those are infrared. Of course, you can't see those because they would be very bothersome, right, if all these lights is flashing around the house. Come on, guys. Oh, yeah. Come on. It's got to go through a cool down cycle before it goes back on. So gallium arsenide phosphide, gallium phosphate, it produces orange light. So I've got blue. Blue's been around. It took them a long time to get blue. Originally, the first two was they were either yellow or red. And then we came out with blue. They had problems with blue because it was pretty close to ultraviolet range. And that's what they was having problems with, is trying to keep it out of ultraviolet range and try to get it white, so it wouldn't hurt you. These are the colors, by the way. So this is just a chart right here that tells us all the colors available to us. And this is not all of them. This came off the internet. I don't remember where I got that, guys. But now we can get them all shades and colors. So these show you the actual colors here. These would be, but then we get into our whites, pale white, cool white, blue, green, lime, yellow. So we got the whole gamut of colors now that's available with LEDs. You can get them just about any color. Well, some of them have special order because these parts places don't carry all these colors, right? Well, white's got to have a used wavelength, because what they had to do with white, what is white? White is a combination of just about all the visible light spectrum, and that's the problem they had. They could dope it to put out one frequency of photon, but how do you figure out how to dope it so you got different chemicals in there, so when they combine, they put out different wavelengths. And that was a big problem they had, to come up with that recipe of what goes into white, to get all these different wavelengths, and then how to get to dope it and put it like that. You can see white has got all kind of, it's silicon carbide, gallium nitride. And this would be the chemical composition there. But once we have something that can emit light besides a light bulb, when we got out of U.S. Steel, they had a line. It was, good gracious, that line might have been, I bet if you stretched it out, the number 4 galvanizer line, I don't know if y'all went out there, that thing was probably over a mile long. But it snaked back and forth. And you're trying to run a strip of 10 strip through there off a roll and keep it perfectly aligned. So they had what they call steering rolls. And what the steering rolls did is, it's going to be all different now, but we didn't have LEDs that would put out white light. So what the steering rolls did, it just had a group of light bulbs down on the bottom. And it had a lot of them. And then on top, it had a bunch of photoresistors. And what would happen if the strip tried to move, then this side, when you added all these together, would have a different output than the other side. And then that would cause the electronics moving the steering wheel to just do what? And the steering wheel didn't do like this. The steering wheel actually tilted. Because if they tilted it, the top would have more friction and it would climb up the road. And if they went the other way, it would climb down the road. And it was really, really neat. Well, now, if they did that, they wouldn't use light bulbs, because what would happen if the light bulb went out? They would probably use what? They'd probably use these white LEDs and then photo transistors instead of photoresistors. But that's what they used up there, a whole gang of photoresistors, which was pretty neat. I saw a video the other day where they had these high-intensity LEDs that was actually lighting a ballpark. And what was so neat about it is they started putting on music, and they were flashing their big lights up there with the music. You can't do that with mercury vapor lights. Have you ever seen mercury vapor? What happens? When you turn them suckers off, you got to let them cool down, and it takes a long time to let them warm back up and start putting out white light. But now they're going to move. We've already seen a lot of tail lights that's using LEDs. Because they got high intensity white LEDs. We got flashlights now that are white, nice white LEDs. We got, on your phone, yeah, your phone's got a white LED back there emitting for you to take pictures. That's the actual flash. And it's not going to be, and you see headlights that are accented with LEDs, which looks really, really sharp, and eventually we're going to have LED headlights. And I'd say we're already moving to LEDs on these LCD monitors. And like I said, you can look at the difference between this guy and then the one that Dwayne's sitting in front of there. Because this is back. And what's nice about this, if you lose an LED, you lose one of your LEDs, you don't lose your whole display. You might get a little tiny dark spot in one spot. You lose that big fluorescent bulb up there, then you what? Yeah, and they're specialized. They're made just right. We got a whole ton of monitors. If you want to know what's wrong with these monitors over here, guess what? What's wrong with them? The bulb's gone out there. Yeah, that's the only thing wrong with them. Got 1, 2, 3, 4, 5. Don't ever buy a planar monitor if you want to buy a new monitor for your computer. Them fuckers are pieces of crap. I think we only got one left. So every one of them was planar in here, 20 of them, and we've lost 20. I think 19. I think we got one back there somewhere that's still working. They probably is. They're probably all working. In fact, you can take a flashlight and you can shine it on it and you can see the pictures. But we don't have time to put them around. We can't give them away either. That's what you think. This is a symbol for a light emitting diode. If it's solid state, it's supposed to have a circle around it, but we lost the circle a long time ago. Sometimes they'll put the little lambda symbol out there. So you may see the circle around it, or you might not see the circle around it. Odds are you're not. So we got the arrows pointing out. And these things come in all shapes and sizes. They arrange them in, I forgot to get this, guys.
I'm gonna leave that thing recording.
These right here are called bar LEDs. They use a lot in volume units, VU meters, if y'all ever in audio. This ain't the real meter. These are called 7-segment LEDs. I'm gonna get some that you can see. These come in 2 configurations that we call a common anode and common cathode. Very popular. So when I come up here and look at my function generator, if you look real close, you'd see these are nothing but what? Those are nothing but what you're looking at. We call these 7-segment LEDs. If you count, because that's what makes up the numbers. Normally they have more than that. They have more diodes in it than that. Most of the time they'll have at least 1 decimal point. Sometimes they have 2. Sometimes they have vertical decimal points. Some of these you might see. The lens, by the way, is the same no matter what. So you might have decimal points on both sides, but because the company might make, you know, common anode, left-hand decimal point or something like that. So, but the lens that they put on is the same. We call these 7-segment LEDs, and you can do a lot. Well, you can make every number, you can make every possible number with groups. So this has got 1, 2, 3, 4, 5 LEDs on it, 7-segment LEDs. Okay. So we got all the colors. The thimble LEDs, they have different lenses. This is what most of y'all see. Auburn's got that Jumbotron down there. You ever see that? That thing is huge. I think it's the biggest one in college football. But all it is just a bunch of LEDs, yeah. So we see these on the side of the road now. These are becoming very, very popular. We used to be amazed. I don't know if you're going down 150. They had that sign down there that had the triangles on it, and it would spin. Every once in a while, it would spin and show a new side of a triangle, and it would have a different sign up there. And people would get mesmerized by that. There was a red light up here, and people they'd wait for it to flip so they could see what was up there. Now it's nothing but a huge monitor. Now they go down there and it's just got a computer in there it's a monitor. That's all it is, a big monitor. And they go in, they connect to it with Wi-Fi, they update a new picture, and they're ready to go. They don't even climb up on the tower anymore to change those signs out. They just get close enough to connect Wi-Fi. And they have been hacked into, by the way. So. Yeah. We have 2 types. We have what we call a common cathode and a common anode. So what we got to do is when they connect the LEDs in the side there, it should make pretty much sense. All we're going to do is turn the light off and on, right? You understand? So we don't need, even though an LED requires 2 conduction, we can make one of them common. And then that will limit the number of pins that I'm going to put on my device, right? You understand? And less control. So they got 2 ways they can hook them up. They can take all the LEDs in there. So I'm just going to draw. And I'm not going to put the little arrows, by the way. And we got 8 of them in there probably, because every one of these have decimal points on it. 1, 2, 3, 4, 5, 6, 7, 8. So what can I do? I can come over here and connect all these together and bring a pin out, connect them inside, and we would call this a what? This would be called common cathode. So we turn a common cathode on with voltage. So what we normally do is we'll come up here and hook this to ground or common, and then we'll come through a resistor. We have to come through a resistor, by the way, just like a diode. You know, you got to protect that diode when you forward bias it, right? Well, we have to do that too. Or I could just as well do what? I could just as well come over here and do it on the opposite side. So I could come over and connect these together and hook them down. And we'll turn these on with common. Still have to have a resistor, and we call this a common anode. That makes sense? So that's what you buy them. CC would be common cathode, CA would be, if the part number starts with CC, it's a what? Common cathode that starts with CA is a common anode. And then we have ICs that do this. We have ICs that take a binary number and displays the results automatically for you. So that's what they're showing us. That's what they're showing you in this slide right here. It's just hard to see. So here they got ground. Normally they do 2 pins, and why they do 2 pins for your common is so you can connect the common up on either side. So we have a big problem with ICs if they put the power pin on one side, and you're trying to hook all these things up, and it's trying to prevent crossing lines. So what they do on the LEDs normally is these are connected together. If I come up and follow them through, I'd see they're just what? They're just connected together. You don't hook up both of them. You just use one of them. Which one is most convenient for you to hook them up? From this side, yeah, you could do that. That'd be good too. So if I put them side by side for displays, what Wesley said is I can bring the ground into one and daisy chain the grounds through the displays. So use ground or power coming in on one, and on the other side, which will be the next LED, I just run it straight over. So we have these star LEDs. Can y'all see these? These are very popular. The problem with 7-segment displays, we can do numbers all day long. It's just that if you try to do letters, it has problems with some letters, right? It could do an A, but a B looks like an A. We could do a lowercase b. We could do a C. We could do a lowercase d. Can't do an uppercase because it looked like a 0. We can do an E. We can do an F. Can kind of do a G. You'll see them come up and do this for a G. So I'll turn on these segments right there. They don't turn on that one. And so you might see that sometimes as a G. We can do a little Y. So we can do this for a little Y. Well, can't do a Q. Can't do an X. Can't do an M. We can do a lowercase n. They just do a lowercase n like this. Most people can figure that out. But the problem is it can't do everything. These star LEDs, you not only can do what? And this is probably, if you got a calculator that displays stuff, it probably uses these guys right here. But it's not using LEDs, it's using liquid crystal. But these liquid crystals, like on watches and everything, they work exactly the same way. Y'all seen these before? These are just a bunch of LEDs, these ticker bars that go displays messages, scroll bars. These are just a bunch of, you can see them here, they're just a bunch of LEDs. Yeah. These are very popular in stores. What we need to do is rule of thumb. If you got the data sheet on the LED to figure out how to hook it up and what resistors that's required, you need to look the thing up in the data sheet. If you don't have the data sheet, rule of thumb is the VF on these things is typically around 2 volts. They could be more, they could be less. I think this guy does it, yeah. So here's the actual VF for these different colors. So this guy gets all the way up to 3.6 or 3.5. Now the resistor you choose will probably work. It's just that the LED would not. If you use 2 volts, the LED won't be as bright as it's supposed to be. That makes sense. So if you got the data sheet and you want to see to calculate the size of that resistor, then what you need to do is look it up, right? And also the other thing we use is you need to know the current that these things are rated at. Usually we try to maybe half this. We very seldom run at their maximum current because if you run them at their maximum current, you're going to limit the life, but don't exceed the rating of the LED. So this guy right here would drop 3.6 volts at 20 milliamps. And this would be a representing the number of lumens, I guess, but they call it MC units, which I'm familiar with. Are we okay? So rule of thumb, if you're just playing around with these things, you don't have the data sheet, these guys are not silicone. They're not going to drop 0.7 of a volt. You are not going to be able to check these things with your meter. The only way you can check these things is to put them in a circuit, or with a light bulb. We used to do it. We used to put a battery in series with our meter and use that to turn them on. So 2 volts DC, rule of thumb, 2 volts DC around 10 milliamps is available. Refer to the LED's data sheet for the maximum VF and the max forward current. When operating in a circuit with a voltage greater than the LED rated VF, a series drop-in resistor is required. So if you got something that's outputting a voltage, you need a resistor. If you got what we call a current source, which we'll look at later on, we can make transistor circuits that output a certain amount of current. So that means if you put one in series, it'll output 10 milliamps. If you put another one in series, it's going to output 10 milliamps, but it'll automatically adjust its current up to the maximum voltage. But we ain't got there yet. Right now, we're just going to turn these things on with voltage. So normally the way we do this is we come in here and we either put the resistor in the cathode or we put it in the anode. It doesn't make any difference. But you're going to have a resistor in series, and you need to calculate that size of that resistor. So if I'm going to come up here and connect this to 15 volts, if we're using rule of thumb, this guy here, so plus we got to forward bias them to come on. If you reverse bias them, they're going to do what? If you hook them up across the power supply, they're going to do what? They're going to burn up just like that. You understand that? Because as soon as they turn on, you got a short circuit. And if you don't have a limited power supply that limits the current, then you're going to have problems. So you don't check these by putting them across a power supply. You can if you put a watt in series with them, a resistor. So what size resistor would I need? So if this guy drops 3 volts, according to Kirchhoff's law, all the voltage in the circuit has to be dropped. So what would this guy here have to drop? It would have to drop 12. We're going to use 10 milliamps, and there you go. Round up or round down. If you know the spec sheets and it's rated at 20 milliamps, odds are you would round up, right? But if it's rated at 10 milliamps, odds are you'll round down to the next standard value. So what size resistor would that be? 12 volts, 10 milliamps. I believe that's going to be a standard value. Because 12 is one of our standard values. We got 1.2K, we got 12 ohms, we got 1.2 ohms, so this is one of our standard value resistors. So what we got, guys? Not hard, this is really simple. 1.2K? Yeah, that sounds right. So that's what we use. That's right on the money. You probably be able to round up, if you looked at those, none of them, all of them is rated at over 10 milliamps, I think, 20, 20, 20, 50. So these guys right here, probably infrared, probably wouldn't work very well. But look, all the rest of them's rated at 20, so rounding up would be fine. If you got infrared though, you need to lower the size of the resistor. So this is how to calculate it. We already know that. So VRS would be equal to VS minus VF max, right? And then we divide that by the current. Y'all okay on that? Oh, here's the common anode and common cathode that I showed you. So the common cathodes, we would turn them on with a voltage. The common anodes, we would turn those on with a common. And we put the resistor in series with each one of them, right? That makes sense? So when you get into digital, if you take digital, we have common cathode drivers and common anode drivers. 7447 is the common anode driver, and 74148 is the common cathode driver. Special purpose diodes with a photodiode. So if we're going to send out the light, then we got to have something to sense them, right? So this is what a photodiode does. So we went over diodes so we could see what the light source was. And then why do we sense the light? How do we sense the light? Well, we sense them with either photodiodes or phototransistors. We'll look at phototransistors. Phototransistors now by far the most popular way to do it. In fact, if you try to find a photodiode, they're even going to be hard to find. They have them what they call pin diodes, but they're pretty expensive. But we'll look and see this. So mostly the predominant method of sensing is using what we call a phototransistor. But this will give us a good idea. So normally, notice they have the little Greek symbol for what? Lambda. Lambda is the Greek symbol for light or wave. It's actually the Greek symbol for wavelength. But since just about all light is given in wavelength, we use that also for light. Or they might have this. This is a standard symbol too. So notice what's going on here. There's a what? Pointing in. Notice how is it put in the circuit? Forward bias or reverse bias? Yeah, so photodiodes are put into the circuit reverse bias. And that's what's happening when the photons come into that depletion region. It's exciting those things and causing them to start move, and they start conducting. But how much they move are going to be, how much opposition goes down is going to be. Now, what advantage does this have over a photoresistor? I don't have my photoresistors out here. Dang it. Put them up. I'll go get one in a minute. But photoresistors are extremely slow. I mean, they are really slow. So it's no big problem. It's no big problem putting them on street lights because how fast does sunlight go up and come down? Very slow, right? But if I'm going to sense something that's moving at extremely high speed, these pulses are extremely high speeds, a photoresistor would never work. But a photodiode was. It's solid state. These guys are really, really fast. So solid state photodiodes and phototransistors are extremely fast. So they can handle just about anything. So even in fiber optics, we use phototransistors for even to sense the information flowing in through there. And we're talking billions of bits per second. A typical photodiode circuit. So what we do, we put a resistor in there, but what we're going to do is we're going to take our output across the resistor, right? We could take it across the diode here, but so when light strikes it, its opposition will go down. Voltage drop across the resistor would do what? Go up. When it sees dark, its opposition would go up, and the output of the resistor would go down. You understand that? So now we got a system. So on this side, we got a photo diode. I mean, we got a light emitting diode. And on this side, we have a what? Over here, we have a photodiode, our photo transistor. And we can couple these things together into a sensor. So this is called an optical interrupter. And you run into these guys all over the place. So what happens over here, it's got emitter. So this would be the LED on this side. Over here, it's got D for detector. So that would be the photodiode on this side, right? Oh, they're all over the place. I mean, they're all over the place. Printers, what they do, I don't know if you've noticed, a lot of times to run your printer, they use what we call a stepping motor. Stepping motors are usually open loop motors. But once they find themselves, when you step it, it steps a precise degrees. So if they start from an origin, then from then on, all we got to do is just count steps. We can either count step it forward or step it backwards, and the position it's at is very, very accurate. So I don't know if you ever noticed, but when you go in there and you boot your computer or you turn your printer on, what do you hear it do? It'll find itself. Well, if you took it apart, odds are on the side it's going to be one of these things. And what happens, it's got a little blade over there that goes there and breaks that beam. And then it steps out a certain amount of steps, and now it knows where it's at. So I don't know if you ever noticed that. So if you restart your computer, you always hear your printer do what? Right? And what's it doing? It's probably finding this little optical interrupter right here. And these guys are used all over. They use these guys to sense speed. What we'll do is we'll have what we call a encoder wheel. The encoder wheel will have a bunch of little holes in it. The encoder will be down between there, and it'll be spinning like crazy, and these things will be just pulsing. And then we'll bring that into either a PLC or bring it into some counters, and then we do what? Then we know how fast something's moving. So we use these guys all over the place. Huh? Good spot. Okay, let's take a break. It takes brought that up. Of course, you wasn't supposed to do that. You're supposed to do this. That was agreed upon. Wasn't that word? Okay. So I should have said you didn't give the sign. The LM3. This is the LM34. Now I don't know if this is Fahrenheit or centigrade. I think the 34 is Fahrenheit, but it's a solid state. It's actually got when you get into electronics, you got to be real careful when you see these 3 terminal devices. A lot of people think they're transistors, but they might not be. They could be a voltage regulator. So that's all the voltage regulator has on his wall. It's 3 terminals. This is actually an integrated circuit, and this is the temperature sensor. So this guy here is very, very accurate. Huh? This is a 3 terminal device, kind of like a Hall. So we got a Hall effect up here. It's got 3 terminals. Our leads, we also call them pins, so they're all used interchangeably. So 3 lead device, or 3 terminal device, or 3 pin device, whichever one you want to call it. It's all lead. Well, anything they can do with 3 terminals, they're going to do with 3 terminals. Right. Oh yeah, that's a standard shape. We call that a TO92 case, which TO stands for transistor outline, but anybody can use the TO92 case. I was trying to get y'all, I don't know if it's a handout or not that shows you all the different types of packages these things can come in. And it's very important that, and they'll come in different variations of the same device might be in more than one package. And if you order the wrong one, you're going to be screwed, right? So you want to order a 3-pin device and you offer a little surface mount variation of that thing. And somebody did that here. That was ordering some transistors. I wish I could find them. And they got all these surface mount devices in it. This is one this is a thermistor, and what I got is I got a little light bulb right here, and I don't know if it'll come on. It's gonna. Huh? No, but you got to be real careful because it'll start avalanching on it. So you can see, y'all see the light on? Can y'all see it? And then y'all can see it start when I cut. All I'm doing is just making this thing temperature go down. Well, no, right now I got it a pretty good well apart. Well, but what happened is the thermistor is dropping a voltage.
Yeah.
So the problem is that if the current running the light bulb gets too high, the thermistor itself will get hot because it's dropping the voltage. If it drops the voltage and we push a current through that voltage drop, it produces power. So you got to be real careful, or this thing will flat run away on you. You'll burn your thermistor up not because it's close to the heat of the bulb, because we're putting current through it. So we can't get very much current out of a thermistor, but we can use it very well as a sensor, right? So if I was to come over here and take the thermistor and just put it in series with a nice resistor like this 10K resistor right here, I mean 1K, I don't have a 10K. 10K would probably be better. And then what we would do, of course, is come up here and hook this thing up. And then all I do is I would use my voltmeter. Of course, we're going to use a voltmeter to show what's going on. But this would be the input to a control circuit or like an A to D converter or something like that. So all I'm going to do is just measure across the resistor. And put this on volts. So now we got voltage. Okay, I got my meter hooked up backwards. But now we got voltage. And when I come over here and put this up, to that. So the voltage across the resistor is going up because the voltage drop across the thermistor is going down. And so now I've got a voltage input that I could use electrically to do something, right? You understand that? So even though so normally these devices that change their resistance with what they measure, all we have to do is just hook a resistor in series with it, and then now we got a voltage divider, right? You understand that? And the voltage divider changes its ratio. So you got one resistor that's going to be fixed, and then one resistor that's changing. So if the resistor that's changing goes down, then the other resistor's voltage drop has got to go up, right? You understand? So now the voltage drop goes up when the temperature goes up. So negative temperature coefficients are very popular because now our resistor gives us a rise in voltage for a rise in temperature. But it's not fast. See that? It's not fast. So if I was going to measure temperature instantly, then odds are this is not the guy I'm going to use. But if I'm measuring the temperature of my house or something like that, and I turn on my air conditioner, it don't jump down to 72 degrees instantly, right? If it's sitting at 80, it's going to do it what? Very, very gradually. So, you know, it's no problem. We can do the same thing with the thermistor, which I've lost again.
What would you use for capacitor feedback?
I don't know what you mean by capacitor feedback.
No. What would you use for a capacitor feedback?
You'd probably use a thermocouple. Thermocouples are real fast, and they produce a voltage that's proportional to temperature. Thermocouples are linear. It's just that they're not solid state, so we don't talk about them in this class. But, we'll talk about, in motor controls, we look at a lot more sensors. We have a class called sensors now, by the way, and we will look at thermocouples. And I was going to do the same thing with that photoresistor and show you that it's not fast, but I have no idea what to do with it. It was here. Now let's get back to this lecture. We could play. So now we got a light source, and we know we can receive it. So I got a light source. I know I can receive it. So what can we do with it now? Well, we can bounce light off things, right? You understand? We can put two things like this optical interrupter. These are fixed. The width between the transmitter and the receiver are fixed, but they don't have to be. So I could come over here and have a light source over here, and then I could have a detector over here, and now when something big moves between it, I know it's there, right? You understand that? So we have what we call through the beam. We have what we call the fused. And we'll go over to the line here in a second and look at these different light sensors. Usually we use them to check proximity. What does proximity mean? When it's at a point. Oh, yeah, it's a point. We have position sensors, but then we have what we call proximity sensors. And proximity sensors don't know where it's at. It just knows when it's at a certain spot. Does that make sense? So that's what we do. So photodiodes, that would be our detector. An LED would be our transmitter. And now we got what we need to do a lot of sensors. So this guy right here we call a through the beam sensor. Because what we're trying to do is we see things when they come through the beam or break the beam, right? What else could we do? This is the optical interrupter we looked at. So we'll pause the lecture and we'll go next door and look at all these different photos. See that? The same symbol that's used for all different types of devices. So but they give you little indications that it's not the same, right? You understand? So this is a symbol for a rectifier diode or a small signal diode. Those use exactly the same thing. Of course, you can tell basically by the size. Your small signal diodes are going to be like the 914 that we played around with. The one in 914 is going to be a little tiny thing. Your rectifier diodes are going to be pretty big. This is a Zener diode. This is a varactor. This is an LED. This is a photodiode, or this symbol right here. So this could have the symbol for lambda, which is the symbol for wavelength. Are we okay? So that's pretty much all we're going to do with transducers. So, any questions? Huh? What we're going to do starting on Tuesday is we're going to start into, there's my photoresistor. We're going to start into, I found my other magnet stuck onto my alligator. We're going to start into chapter 9. Page 2, what's that? What's the title of it? Bipolar BJTs. So when you hear transformers, transistors, we have two types. We got BJTs, and then we got FETs, which are the field effect transistors. So we'll look at the BJTs first. These are your high current, high speed devices. And then we'll look at your FETs, which are your low power, low current devices. Are we okay? All right, I'm going to go ahead and take another break, and I'll run off this diode lab for y'all, and we'll work on that first, and y'all can go back to the lab that y'all are working on. No questions?